Assalamualaikum warahmatullahi wabarakatuh. We meet again. This is you know the 10th meeting maybe, and then uh, the second meeting after the mid semester examination. And for this meeting, we will discuss about something that's maybe still related to the analog thing, but we cannot consider this as as the same thing because we will discuss about pulse width modulation, pulse and also drum controller. But it is a little bit related to the analog thing because sometimes when we want to control the analog output, we use PWM or PWM. And why is that? Because we want to control the analog actuator using a digital output. So the PWM here or PWM or pulse width modulation here is something that is very commonly used to control something. But if we didn't have an analog output for that, we can use a digital output by manipulating the pulse. The width of the pulse, hence the name of pulse width modulation. Okay, so I just want to share a little bit about the pulse width width modulation here. So if you want to control, for example, the light intensity or the velocity of the motor, servo motor, we can use an analog output. For example, we can connect the analog output to the lamp or maybe to the DC servo motor, and by doing that, we can control the light intensity or maybe the velocity of the DC motor servo. But sometimes when we only have digital output, when we didn't have an analog output, we cannot control using the analog output because we didn't have one. We didn't have one. So instead, we want to control the intensity or maybe the speed or maybe the flow, something that is not related to 1 or 0 or logic high or logic low or logic 1 or logic 0 by using pulse width modulation, PWM. Why? Yeah, because we can also control many things using PWM. If you're familiar with a microcontroller, especially the Arduino, you can notice that some of the Arduino didn't have an analog output port or pin in its device. Because if we want to control something analog using Arduino, we use PWM or PWM, and we can connect it to the pin that is connected to the actuator outside. And in this case, in PLC, we also can do the same. We can control many things using pulse width modulation. Last week, we already learned that we can attach many analog modules into a PLC device, and we can control many analog things. So this is the chance of thinking. Usually, we can relate it to a PLC with something that is controlling an on and off device. We usually think that, okay, using the PLC, using a digital output, we can control whether the lamp is on or off, whether the motor is on or off, or maybe whether the flow is on or off. Anything. It is always between on or off using digital device. And last week, we can also understand that there is more than that. We can also controlling something that is not only on and off, but we give the value for that something. We can control opening valve, how how much space that the valve must be open. It can be 30%, 50%, 40%, 55%, 49%. So the range can be from 0% until 100%. It is the same with lamp. Before, usually we control the lamp, the intensity, by making a lamp is on or off. The lamp is on. It means that the output accepted logic 1 from the input. The lamp is off. It means that the output accepted logic 0 from its input. But using an analog output, we can control the intensity of the lamp. It can be very bright, the intensity. It can be, almost dark, or maybe between dark and bright, almost bright, half bright. Yeah, we can control many situations using the same output. And as I previously told you that it is not always the case. Why? Because sometimes, yes, sometimes we didn't have an analog output. So, for example, here, what if, what if we want to control an analog output? For example, I just want to choose the easiest one because we usually work with lamp. I just want to control the intensity of the lamp, but I only have digital input and digital output. And in this case, we can actually see that we usually have analog inputs, but there is no analog output here. And of course, because we only want to control one lamp or one intensity, it is not very practical. It is not very practical to buy an analog module. Why? Because this is a PLC. Even though I already say to you that it is not that expensive, but it is still quite expensive compared to microcontroller or maybe other type of controller. The PLC still can be considered pricey. So how do we control something that requires many chains for the output using digital outputs? And the answer is by using pulse width modulation. It's very common. Okay, but we have to understand that this pulse width modulation can only be used in Type T PLC. I already previously told you what is the meaning of Type T PLC. This is the transistor PLC, solid state. So it means that it can give a high amount or number of frequencies. So it can change from logic 0 to logic 1 rapidly. It is not something that can be done using our type of PLC. There are three types of PLC, output-wise: Type T transistor, Type R, and Type U universal. So this thing can only be used in Type T PLC transistor. And the port output is dedicated at %Q 0.0 and %Q 0.1. So unfortunately, we cannot use more than two pulse width modulation in this type of PLC. Maximum, there are only two output that we can use. Maximum, there are only two output. So we have to, we have to use %Q 0.0 and %Q 0.1. But we have to be careful here because, yes, because if we use pulse PLS, which is different type of functioning in this PLC, we have to share with it. So if we want to use PWM and also pulse PLS, we cannot use for both of them for these two devices. So in this case, one can be used for PWM and one for the PLS. This is the limitations of using the PWM or PWM in this files. This is very unfortunate, but maybe we don't really have to, have to use both PWM or Pulse. Usually, we only want to use this one device. Okay, so we can see it here for the specification of PWM. The specification of PWM here. The number of channel is 2, which means that, yeah, we can only use two output for this, namely %Q 0.0 and %Q 0.1. And the minimum frequency is 1 Hertz. It means that if you already know how the PWM works, it means that the period is 1 second, because 1 divided by the frequency is equivalent with the periods. Okay, it's equivalent with the periods. And the maximum frequency is 10,000 Hertz, which means that the minimum period is 0.00001 second. And the accuracy on frequency is 1%. Maybe it's still a little bit confusing for you all. So I have to show you the sequential chart. Okay, so this is how we use the PWM. We can see it here that this is the output. The output can be between logic 0 in this case, in this the first step, the situation or the logic for the %Q 0.0 is 0. It means that it gives almost nothing to the output. And then we give the %PWM 0.R 20%. It means that the duty cycle is 20%. And it raises another question: what is the duty cycle? But it basically, the duty cycle is the the comparison between the high logic or the logic 1 with all of the logic, which is the adding logic 1 and logic 0, and then 20% of all the situation is high. We can see it here. So if we use 1 second period, it means that 0.2 seconds is logic high or logic 1, and 0.8 second is logic 0 or logic pulse. It is for 1 second. What if we use 1 millisecond period? It is the same. If the duty cycle is 20%, it means that 0.2 millisecond is logic high or logic 1, and 0.8 millisecond is logic 0 or logic low. So how this is related to the output that we can control? It is very simple actually. Duty cycle means that the maximum, the quantity of the output that is being measured. For example, if you use the duty cycle 20% and then you want to apply it to the lamp, it means that the intensity of the lamp will reach 20% maximum of the maximum intensity that the lamp can be given. Or maybe if we connect it to DC servo motor, for example, the maximum speed of DC servo motor is 100 rotation per minute, and we connect it to the PWM from the PLC, which has 20% duty cycle. It means that the velocity of the same servo motor will reach maximum 20 rotation per minute, because it is multiplication from duty cycle with the maximum velocity of the motor DC. 0.2 multiplied by 100 is equivalent with 20 rotation per minute. So we can see it here that this is the chart that show us the relationship between the logic 0 and 1 with all of the periods here. So if the duty cycle that is controlled, that is specified by the percent PWM 0.R is 20%, the sequential chart will be like this. The high is only 20%. But if we change the duty cycle until 50%, it means that the high and low is equivalent with 50% of the maximum period. And if we arrive at the duty cycle at 80%, it means that the logic high will have 80% of the maximum period. So if for example, if the period 1 second, if the duty cycle 80%, it means that the logic high will have 0.8 seconds from all of the 1 second period. So this is the sequential chart. So we will have to go back to the definition again. Duty cycle, which means the high amount percentage in one period. And how we define the periods, we can use the frequency there. We can just give the frequency that we want when we adjusting the setting. And then the relations between the percentage and the duty cycle is the percentage will determine the intensity of the light or velocity of the motorcycle. This is for the duty cycle. So we can, make so many applications with this. Even though we can make everything easier by connecting the analog output to the PLC compact, because it means that we don't have to use the PWM. But the PWM can come in handy when we didn't have analog output that can be attached to the PLC. So in this case, we can still control many things using the PLC. Because in the modern usage, if we want to use the control closed loop, sometimes we want to measure things in closed loop, which means that we want to know we want to know and compare the output with the input and make sure that the output meet the requirement that is given by the set point. So in this case, if we want to measure it, we have to connect a sensor to the output, and then we just want to translate everything into a voltage or current, and then the current or the voltage will connect it to the input of the PLC. And by doing that, we can make a closed loop control. And in the PLC, we can create many programs to adjust the controller setting. We can use a fuzzy logic. We can use PID control, two of the most popular controller in the industry, especially the PID. But we can use PWM, and we don't have to use the analog output. Okay, so this is to set the PWM. Yes, to set the PWM. We can see that this is the type of the PLC that we usually use, TM221CE16R. But we can see that this is the type of the PLC that we use if we want to control using PWM or PWM, or pulse width modulation. And this type is TM221CE16T. This is the type of T. So the limitation is actually we cannot use to control an alternating current voltage. We can only use control direct current. And it is okay. It's okay. So we can see it here that we can use pulse generator. This is the pulse generator here. And if we want to configure here, we can use and choose PWM. So we can see it here that the pulse generator, we only have to, and we have to choose between these four. So we cannot we cannot use all of this type at the same time. We have to use and choose. And if we choose PWM here, we have to define the time base and also the preset. If we multiply the time base with the preset, we will get the period. If we divide 1 with the period, we will get the frequency. So we can see it here that the time base can vary from 0.1 milliseconds, which is equivalent with 10,000 frequency, to 1 second, which is equivalent with 1 hertz frequency. So we will back again. The minimum frequency is 1 hertz. We will get it if the time base is 1 second and the preset is 1. So it means that the period will be 1 second and the frequency will be 1 divided by 1, which is 1 hertz. And also, we can use frequency 10,000 hertz, which means that the time base must be 0.1 millisecond and the preset is 1. And it means that the period is 0.1 millisecond. And it means that the frequency is 1 divided by 0.1 millisecond, or 10,000 hertz. Okay, I just want to use something that is very common here, maybe 100 millisecond or 0.1 second. This is for the pulse width modulation. So in this case, we already configure the pulse with modulation here, which is very simple. But we have to keep it in your mind that we only have two for all of this type: pulse, PWM, PTO, and frequency generation. So if we want to use these two outputs for pulse width modulation, it also means that other type of syntax in this case, which is pulse and also PTO and frequency generator, cannot be used. Unfortunately, only two of them. So it's okay. Okay, so if we want to use the pulse width modulation here, okay, I just want to delete it here. You can see here. This is the pulse width modulation. So this is almost in the same criteria with timer counter in the same box, but you choose here pulse width modulation. And we can see it here that the time base is 10 milliseconds and the preset is 10. It means that the frequency or the period is 1000 milliseconds or 0.1 second. So the frequency is 10 hertz. Okay. Okay, so this is how we create the ladder diagram for the pulse width modulation. It is very, very, very easy. And we don't have to define the output here. Like I previously told you that the output is defined by the pulse width modulation. It means that if you use this address for the pulse width modulation, in this case percent PWM0, the output will be in percent Q0.0. But you don't have to put percent Q0.0 here because it will be automatically given. So where you can get it, you can see it here. When we use percent PWM0, the dedicated output has already defined. So it means that we don't have to worry to put the address percent Q0.0 here because the program will already dot this to you. But the important thing is that to give the duty cycle. Why? Because we have to define the duty cycle in order to make the PWM work. But it is very easy. So this is how we define the duty cycle. So this zero run here, we create the pulse width modulation. And this first run, we create the duty cycle for the pulse width modulation, which means that the 10% of the pulse will be logic 1 or logic high. So if we connect the output, in this case percent Q0.0 to the lamp, and the duty cycle is 10%, it means that the chart will be like this. One period, this is one period. Time for the one period by using this configuration is 0.1 second. So this will be 0.1 second. The time for one full wave. wave, logic 1 and logic 0 is 0.1 second. Why? Because the time base multiply what time preset is 100 millisecond, which means 0.1 second. So 0.1 second will consist all of the logic from logic high to logic 0 here. And then the 10% of that from the range of 0.1 second will be a logic high, and 19% will be logic 0, which means that the logic 1 will consist 0.01 second, and logic 0 will consist 0.09 second. And it means that if we connect it to the lamp, the maximum intensity for the lamp will be 10% maximum. So if the lamp produces maximum 1000 candles, if we connect this PWM to that lamp, the candles or the intensity of the lamp will only be maximum at 1000 candles. Okay, so this is basically how we create, pulse with modulation. It is very easy. It is very easy. But the most important thing is that we know when we use it, or how we use it, or why we use it. That's the most important thing. So it is no longer something that's logic 1 or logic 0, or it is on or it is off, but we add the intensity or the value of the output here in order to make something work. Why? And because the system required us to do that. And it is very popular if you want to use the closed loop control system. Because we have to make sure, for example, if we want to control the intensity, we have to make sure that the output meet the requirement. If the requirement is 50% candles, it means that the output must be 50%. If the output didn't touch that number, we can use closed loop control to adjust the number in order to be as closely as possible with the 50. Okay, so there is a configuration for PWM, and then what if we want to use pulse? So the purpose of pulse and PWM is quite different. It's quite different. The purpose of the pulse is just to count the pulse. So PLS, the simple way or the simple device that is connected to the output here. It is more simple than pulse with modulation. So in this case, we can choose pulse here. And because we use the %PLS1, the output is dedicated to the %Q0.1 or %Q0, dot 1. And the time base, we can control it. It's almost the same, and the preset, we can also control it. And the behavior can be double word or a single word or integer or not. But the purpose is different. So if you want to use the pulse here, you can use this. You can see it here. time base 1 second. The preset is 1. It means that it will produce the high and low output for 50% duty cycle. Okay, so this is the case, and we can count that. We can count that. And if this is the thing that is related to the counting thing, the function is almost similar with the counter. But we count the pulse, not the logic 1 or the logic 0. We count how many times the pulse is active. And this is how we use the pulse. So it's very easy. Maybe the next challenging things as when we use a drum controller. Yes. So after we use the PWM to controlling analog output using digital port, and then we move to the pulse when we create something that is similar with PWM, but in this case we use the pulse to count the output. And then there is a drum controller which control the output that will be active based on the step, and we can configure it to control a number of outputs. So it's quite a little bit easy to use, but we have to be careful here. Okay, I just want to delete all this. Okay, we want to use the drum controller here. We can control the step and the output. For example, we use M0 here and M1 here. And if it's full, it means that the full output will be active. If it is reset, it means that it will reset the step to step 0. And full means advance one step. How we configure it, maybe it will be better if we try this. For example, we use this percent Q000. We cannot use it because it is being used by the PWM, so yeah, you have to be careful. Okay, because I just want to use as many input as I want. I just want to undone the PWM inputs. I just want to use all of the outputs here. So I just want to use all of the output. We can use multiple output with the same address. Maybe until this. Now we cannot use keynote to 7. Number of step is just 7 or 8 is okay. 9 is impossible. Okay. What if we want to use 50? Maximum is 8. Okay, so what is need? I just want to make this clear. Okay, this is the drum 0. So we can see that there are 8 steps here from step 0 until step 7, and we configure 7 output, but we give the output two times. So the situation will be like this. For the first step, percent Q0.0 will be active. And then for the step 1, percent Q0.1 will be active. For the step 2, percent Q0.2 will be active. And then for the step 3, percent Q0.3. For the step 4, percent Q0.4. For the step 5, you can see it here. It's correlated to the agreement sign here. Okay. So whenever we activate the M1, it will be active like that. So I just want to launch the simulator here. Because we cannot see the percent Q output. We cannot see it. So we have to use the simulator. Okay. So we can see it here that at the very beginning, the output 0 is active. And why is that? Because at the step 0, percent Q 0.0 is active. What if we add the step? The step 1, 0.1 will be active. You can see it here. And then we can just give step 2. Yes, there is nothing active. Why is that? Step 2, Q0.2 is active, but there are conflict here. It's okay. Step 3, the output 3 will be active. Step 4, the output 4. Step 5, the output 5. Step 6, the output 6. Step 7, the output 2. And it will be back to 0 again. So it will be, back to 0 after it's reached maximum step. So you can see it here. The color is changed here. Color is changing here. Okay, at the step 1, there is conflict here. Okay, what happens if we push the reset? It will exactly make the step back to 0 again. So no matter what the situation here, if we press the reset, we will be back to 0 again. Steps. Okay, so I just want to show you this. And then I just want to see a different configuration. And in this case, I just want to use this output. File still running. Stop simulator. Okay, so the simulator is still on, so we have to stop it in order to configure this from the very beginning again. I just want to change the number of steps here. Okay, we want to see what this configuration will make. So we can see it here that at the 0 step, the output 0, 3, and 5 is already active. For the first step, 1, 3, and 6, everything is changed. And then after it's reached number maximum, it will active here, the NIT here. So we can make it back from the very beginning again. So we can see it here that the output is strictly active based on this configuration that we already created before. And it's very easy to use. It's very easy to use. Okay, so what kind of output that you want to make active in every step, and you can just create it here. So it is easier to use than use the manual or maybe the conservative way to make it output work. And you don't have to worry here, even though you don't create this output. For example, you don't create this kind of output here because we already configured it here. It will active. It will active because we can see it here from the simulation. The output is active, even though the address is not shown here. The address is not shown here in the ladder diagram. But if you connect the output, of the PLC to maybe to lamp, the easiest way, the lamp will be active based on the step here. So I just want to show you what happened if we put a number of resetting here. Just want to stop the simulator again. And then I just want to put percent %M0 here. At the maybe the third step is what happened after this. Okay, we step one, step two, step three, and we back to zero. So we have to be careful here. Why this is happening? Because we put the address of M0 at the third step, and M0 is connected to the resetting here. So when you make this active, the drum controller will be back to zero again. And because it is back to zero again, the counting will be start again. Even though it hasn't come until full number, until 7 and 8. Because we accidentally put the percent %M0 at the drum controller. And then I just want to know what if we put M1 instead. M1. Here we call it 0, 1, 2, and we can see that this is active because it reached maximum. Minor things happen. At the third step, it will stay true. So you have to click to set to zero again and then put it again. And everything will be back to normal after that. So this is how we use the drum controller to control many outputs at the same time. And I just want to emphasize that this is very, very simple and it makes our program easier because the same thing can actually program using different syntax or different configuration. Yes, but it will be much harder and much complicated. So maybe for the homework, I will give it to you for the assignment. I just want you to compare two different uh, way of programming. One is using a drum controller, and the other using the normal programming. And then you can see whether the drum controller will be so much easier compared to the conventional programming. And so the assignment, one of the assignment will consist of programming, and we use two different ways of programming for the same assignment. One is using the drum controller, and the second using the normal programming using ladder diagram and many. And so this is uh, the subject for our meeting today. I hope that you understand this, yes, because yeah, maybe for the next week we will try different application of the PLC. So before the mid semester or mid examination, everything is from logic 1 to logic 0 that makes a certain output active. Maybe after we use the counter or use the timer. But maybe for the few next week, several weeks, we want to apply the program into a real plan. The real plan in order to make everything works fine and perfectly. So it is no longer controlling one lamp or two lamp or so many lamps or maybe one output or two output, but how we interpret the system and make the simplest program in order to make the system work. So we want to try to simulate the real situation, the real plan using the PLC. But it is for next week. For this week, we already learned how to use the PWM and a little bit about the pulse and also how we use the drum controller that is actually makes controlling many outputs easier. And there will be an assignment for that to compare the different way of programming using the drum controller and using the normal programming. Okay, so this is for today. Any questions? Any questions?
I have a question, sir.
Yes.
Uh, how about uh, the memory consumption?
The memory consumption
Yeah.
will be less in using the drum controller compared to using the normal programming. Because in the drum controller, we use less RAM. You can see it here that in the drum controller, you can only use one or two RAM. But maybe for the same programming situation, when we didn't use the drum controller, we can use many rungs. For example, maybe 8 rungs or 9 or 10 rungs. So the memory will be less or smaller compared to using the normal programming. So there are many advantages of using the drum controller or the special output input thing in the PLC because they created for a purpose. And if we can use that, we can simplify many things and also reduce the memory that is required to make the same program. Okay, I hope that this is clear. Is there still any questions? Okay, if there is no more question, so I just want to end the meeting today. I hope that you all understand this, and I will give the assignment to you maybe after this, and also the link for the video recording in YouTube and also in the Google Drive. And you can access it also with the subject or the materials that I already shared to you. Okay, so this is for today. I hope that you enjoy it. Assalamualaikum warahmatullahi